Okay, functions and graphs. So, chapter 5. Alright, now, as required, so date 5th. Alright, please bring your notes to every lesson. So you should have a sleeve or folder as part of your, when you bring your textbook and your exercise book, etc. Please bring the notes with you. I'm not seeing very many in front of you because I need you to actually look at it and refer to things going on here. Okay, so this section will mainly be covering the graphs, okay, so things like parabolas and straight line graphs that you would have done in the last couple of years. Okay, it's also going to be introducing circle graphs. It's also going to be introducing hyperbolas, cubics. Have you come across those in the last couple of years? Not really? Yeah. You have? Alright. So basically you've got an equation and you are asked to graph that equation. Okay, so we've done a whole topic of equation. Okay, so the skills that you have learnt in that chapter is relevant to what we're going to be doing in this chapter. Okay, and we're also going to be learning of a new notation which is called function notation. Now, one thing I will point out now, has anyone heard of the program GeoGebra? Yes. Okay, right. It is a free download on your computers. There is an Apple app. I'm sure there will be an Android app as well, and it's free. Alright, and it's a really good graphing software. Okay, so on your computers, on your tablets, on your phones even, okay, that'll be a very, very useful download to have. What you can do is you can put the equation of, you put the equation down, y equals something in relation to x, and it will graph it for you. Okay, and that will give you some feedback in terms of what the graph should look like. Okay, how steep, how wide, etc., etc. Okay, and I will be referring to it quite a lot, this topic. Okay, now because I don't have my laptop connected, I'm not going to use up any more time now. I'll be going to use that quite a bit, this topic. Okay, so GeoGebra. Okay, download the app, download the program, whatever you want to call it, and we'll be referencing that a lot. Okay, GeoGebra. So pretty much a combination of geometry and algebra. Okay, so 5.1, function. Alright, also GeoGebra is useful when you're doing your questions for your homework task, instead of going back to check the answers in the back of the book, because quite a few people here have identified that the answers aren't always correct in the back. Okay, all you have to do is substitute that, put that equation in the input bar, and it'll graph it for you.
Correct the answer in the book.
Hey?
Change the answer.
No.
It makes the rest of the book confused.
Because once I actually find the time, which I'm really struggling with at the moment, to do some of the questions in your exercises, I'll be able to see which ones are incorrect. Yeah. Okay, and they'll be the ones I'll be looking for when I'm checking your work. Okay? Lucky for you so far, I haven't found them yet. Alright, functions. Alright, so I'm going to read through the notes here. So everyone on page 33. And reading along. Alright, so a function can be considered as the representation of an equation in graphical form. So when we graph the equation, so where we have a straight line, a parabola, a circle graph, a hyperbola. We're also looking at absolute value graphs, okay? These are all functions, all right? What's unique to a function, which we call f, compared to all graphical forms of equation, is that there is only one y value for every single x value, okay? I'll talk more about that in a moment. Right, the dependence on on f and on x is made explicit by using the notation f of x. So, for example, if we have equation y equals 2x plus 4. Alright, we're now introducing a new notation. So it is now f of x is equal to 2x plus 4. Alright, so instead of calling it y equals, it'll be now notated as f of x. Okay, the function of x is here. Alright, if I had the function of z, alright, it would be 2z plus 4. Alright, it is an expression relating to the variable inside the bracket. And this is called function notation. Okay, so in other words, we are used to equations in the form y equals 2x plus 5. Using function notation, so I've done a very similar one there, the equation becomes our function of x equals 2x plus 5. So, in other words, when I graph this, okay, we should hopefully all know it's a straight line with a positive gradient and a positive y-intercept. Okay, we would normally go x and y to label the axes. Okay, now the x will still be there, however, this will be labelled as your f of x. Alright, so just a couple of tweaks so that we're introducing what we are getting to function notation. Okay, any questions so far? Right, domain and range. Have we talked about domain and range when you're graphing last couple of years? Okay, so the set of real numbers x on which f is defined, which the function is defined, is called the domain. Okay, so the domain is all the possible values of x that you can have for the function. Okay, in this example, you could have every single value of x because the line is a continuous straight line. Okay, the set of values for the function of x obtained as x varies. So in other words, when you are plugging in the x value into the equation, alright, you are going to get the corresponding y values to do the graph. Okay, those y values are called the range. So all the possible y values you can have for the function. And in this case of a straight line, you can have every single y value. Okay, because every single x value exists will result in every single y value also existing. Okay, right. Now we'll cover more on that in a moment. I'm just giving you a bit of an overview and then we'll look at the specifics. Okay, right. Dependent and independent variable. Alright, this x here. Alright, so let's do it again. Y equals 2x plus 4. The x, okay, so the x is the independent because the value of x is not dependent on the value of y. Okay, so here in my equation, it's the other way around. My value for y depends on what I substitute in for x. Okay, that makes y the dependent variable because it depends on the other variable to give the value. Okay, say it again. The x is independent because it does not depend on this y value, right? Because it's its own function on the other side. And if you were graphing, you'd be doing a table of value. You'd be substituting in for the x value, okay, so that you can draw the graph, all right? And that's what we're referring to as independent. The y value, because the equation of the y here depends on what value of x that you substitute in, okay, that is why it's referred to as the dependent variable. Okay, so y or f of x is called the dependent variable since it depends, value depends on the value chosen for x. Right, so putting in more simple terms and what you should be already used to. So put in more simple terms, for the above equation, y equals 2x plus 5, if we were to graph this, we would use a table of values. Okay? So x, y, and then you would pick at least 3 x values, okay, in your table of values to get the corresponding y values. Alright, so let's change this to 2x plus 5 just so it matches the notes. Okay, so the x value does not depend on the y value, so we say the x value is independent. Okay, the y value will depend, so this value depends on the value above it to complete our table of value. Likewise, all these values for y, they will depend on the x value that you put into that table to get a value for y. Okay. Now, for those people who do physics and chemistry, is there anyone here that does not do at least one of those? That you don't do physics or chemistry? No. So, in physical phenomena, okay, when you are graphing, so you might have done an experiment, etc., okay, to represent the warming of water over time, okay, or how fast an object falls to the ground, the speed of an object as the time continues, for example, and you ask to graph that. Okay, the independent variable, okay, so where you would normally do your y or your f of x, okay, the independent variable is always graphed, sorry, the dependent variable is always graphed on the vertical axis. Can we change those notes because I've got them back to front? The dependent variable, okay, so about halfway down the page, underneath the table, the second paragraph, can you change that independent to dependent, please? Okay, so the dependent variable f of x or y is graphed on the vertical axis. The independent variable x is graphed on the horizontal. Okay, so independent and dependent. Okay, so relating to your time here, for example, okay, so whether how quickly water boils over time or when something falls out of the sky and you're measuring the speed, okay, that time is independent because you are measuring that and that will then depend on the speed or the temperature, whatever you're graphing on this axis here. Okay, so that'll be the connection to your physics and chemistry and probably even biology. Biology?
No.
You don't do any science at all?
Nope.
Wow. What about you? I don't meet many students these days that don't have any science course.
Hey sir, nice to meet you.
Okay. Any questions so far? That's probably a bit to take in. Is there anything people not sure about or would like to ask before I move on? Okay, it'll make more sense as we do, progress further into the topic. Alright, next section, vertical line test. Okay, so this is relation to whether we have what's called a function or we don't have a function. Okay, so at the very start I said the function in graphical form means for every single x value there's only one y value. Okay, so every single x value there's only one y value. Okay, what we can do graphically, and you'll see this in your exercise 5.1, just considering general applications of that. Alright, hopefully that'll make more sense to you then. Okay, so the vertical line test. So if a vertical line cuts the graph only once anywhere along the domain, okay, so any x value, the domain is all the x values that the graph can represent. Okay, if that vertical line cuts the graph more than once, okay, then the graph is not a function. Okay, let's do some examples to try and make some more sense of that. Alright, A. So the question, are the following graphs function? Alright, just do a quick sketch. We have a nice parabola there. So we are determining whether we have function or not. It is very warm. Probably the heater's still on. I'm going to go try and turn it off, maybe turn the fans on. Okay, so if on that parabola I can draw a vertical line anywhere and it only cuts the graph once. Okay, so I'm just going to just insert some vertical line. So let's put one here. Vertical line. Okay. This vertical line only cuts the graph at one point. Okay. If I move the vertical line here, again, it only cuts the graph at one point. So anywhere along the domain, so that's going along the x-axis, that I can put a vertical line, anywhere I do that, it will only cut the graph at one point. Okay, can everyone understand what I'm saying here? Okay, only one point. So therefore, yes, this is a function. Because every single value for x has a value for y. Alright, second one. We have, alright, a bit hard to see in your notes. Okay, so what I have is an open circle here and a closed circle directly under it and a horizontal line going either way. Can you add arrowheads here, please? Just one thing I can't do with GeoGebra, add arrowheads at the moment. Okay. So again, if I do my vertical line test, okay, so I'll start way over here. Alright, anywhere I put a vertical line, it's only going to cut the graph at one point only. Okay, so if I start here, I'll put that vertical line there, it's only going to cut this at one point here. Alright, anywhere I put that vertical line, so again, cut there, it only cuts the graph once. If I go back the other way, alright, once, once, once. Now, we have to be careful with this point here. So that's a closed circle. That means this part of the graph is also including that specific point. Alright? An open circle, like your inequalities, okay, remember how we graph using inequalities? There's closed circles and open circles for whether we have equal components or not. That means this part of the graph is not including that specific point there.
So if they were too close, they wouldn't be a function.
Exactly, alright? So, because there's one open circle, if I put the vertical line here, that first point is not considered, okay, because it's an open circle. However, the closed circle down the bottom here is part of the function because it's also included for that specific point there. Amanda has said if they were both closed, okay, it will not represent a function because if I put the vertical line there, there will be two places on the graph that line crosses. Okay, now because the open circle here, we have yes, this is the function. Let's go back the other way. If this was open and also if this was open, would the vertical line test satisfy? No, because if I put the vertical line here and here with an open circle, okay, that means the graph, the vertical line does not cross anywhere on the graph. So if you have that, it will not be a function. Okay, and we'll talk more about that as the topic develops. Alright, but for the example you are given, it is a function because every single vertical line you can put across the whole domain does cut the graph at exactly one point. Okay, if it's more than one or it's zero anywhere, then the graph is not a function. Okay, so we're just getting our heads around it and then it'll make more and more sense as we develop into the topic. Alright, C. Have we done circle graphs in the last couple of years? Okay, we're doing a fair bit of that coming up soon. Alright, circle.
Good circle.
Youth practice. Okay, so now thinking about anywhere you can place that vertical line on that domain. Alright, do we or do we not have a function? No, okay. So, this domain is restricted because the graph is restricted to these values here and here. So, firstly, if I put the ruler way out here, that vertical line test will fail because the graph doesn't go out there. If I put it right here, extension 1 students, if I put a tangent there, it would satisfy, okay? If I do inside here a secant, extension 1 student, okay, it cuts the graph in 2 places, okay? So everywhere along the domain, okay, it can only touch at 1 point. Alright, so if we draw a vertical line here, okay, it'll fail and is not a function because it intercepts at 2 points. So no, it is not a function.
I don't want a whole group.
I know, they brought out a whole course runs without the cross.
So just fruit
Yeah,
ones. They've
no,
had
no,
those
no,
for
no,
ages.
no, the chocolate ones.
Oh, they taste really bad.
They do,
Taste them.
except for when you have,
Nutella.
chocolate chips with them.
Oh,
Absolutely.
Anyways, back on task.
I don't know.
Alright, so they're graphical forms and this is what we're going to be looking at as part of your graphing technique. Alright, any questions before going to D?
There is a, oh, there is
Is there a thing?
Yep, on the next page.
A.
Alright, so here's your equation. If f of x is equal to 2x plus 5. Alright, so now we're looking at function notation. Alright, so remember, you guys would have been used to this being y equals 2x plus 5. Alright, so we are now changing the notation to become a function of x. And the function of x is 2x plus 5. So, the question says, find f of 2. Right? So what this means, every time there's an x in this equation, you replace it with a 2. So it'll be 2 times 2 plus 5.
9.
So, like a table of values, when x is 2, the y value is 9. Alright, f of 5. So, every time there's an x, I replace it with what's inside that bracket, a 5. 2 times 5 plus 5. Okay, which is 15. So when x is 5, the y value is 15. Lastly, f of negative 3. Okay, so that means in the equation, I replace x with negative 3. The negative 6 plus 5, negative 1. Okay, these sort of things will make more sense in the application when we get after these couple of exercises. Alright, E. You now have the following. F of x can represent 3 things. So, negative 2x if x is less than negative 1. It is also x plus 3 if negative 1 which is less than or equal to x which is less than or equal to 3. And it equals 6 if x is greater than 3. So, this example B, the graph done there will be coming from something of this nature, okay? So yes, we will be able to get the skill to be able to graph this. It comes from something along that line, okay? And we'll look at that when we come up to it. Alright, so the question asks you to find f of -3. Sorry, f of -3 plus f of 0 plus f of 5. Okay, so we need to find those three values and add them together. So let's do it bit by bit. So first we'll do f of 3, -3, sorry. So which of the three equations would I be using? Okay, so we're looking at the domains. These are the domains for the specific graph. So -3, which is less than -1, but that's my equation. Okay, which will be -2, lots of -3. Okay, 2 negatives make a positive. 2 times 3 is 6. F of 0. So which domain on the right over here does 0 lie in? Middle one, okay, because it's between -1 and 3. So we have 0 to replace the x with what's inside that bracket. We have 3. F of 5, which of the three equations? Okay, so 5, which is greater than 3, so we have this equation. So a constant number is still some function of x. Okay, just has no variables in there at all. It's always going to be 6 for every single value greater than 3. Right, so f of -3 plus f of 0 plus f of 5 is going to be 6 plus 3 plus 6. 15. Right, question. Alright, so a bit to take in then, so I'm going to stop there. That is exercises 5.1 and 5.2. Alright, so yes, you have an assessment coming up. You still need to be keeping on top of your coursework while still getting that time to revise, ready for your assessments. Okay, so all that geometry stuff needs to be done as well soon, because I'm still deciding on the due date. Okay, any questions?